Okay, welcome back, students. We are continuing with electromagnetic field theory, and in that also we are continuing with Maxwell's equation. Okay, so just a quick revision. We are talking about Maxwell's equations in differential and integral form. We revised about Gauss's law of electrostatics, Gauss's law of magnetostatics, Faraday's law of electromagnetic induction, NPS-Circuital law, Gauss divergence theorem, Stokes theorem, application of EM waves. Then we also talked about electromagnetic waves, Maxwell's first equation. Then we started talking about electromagnetic field theory, in which I told you all that all the four Maxwell's equations are representing the basic laws. Okay, like Maxwell's first equation represents Gauss's law of electrostatics, Maxwell's second equation, Gauss's law of magnetostatics, third equation, Faraday's law, fourth equation, Ampere-Circuital. We derived Maxwell's first equation in differential form in the last video. Okay, this was Maxwell's first equation in differential form. Now, in today's video, we are going to derive Maxwell's second equation. So now let us write down today's topic. Be ready with your pen and page. Maxwell's second equation in differential form. Okay, so Maxwell's second equation in differential form signifies, it represents the Gauss's law of magnetism or magnetostatics. And what is Gauss's law of magnetism? The surface integral of magnetic flux density over a closed surface is zero. So we know that magnetic lines of force are in the form of closed curves. That is, neither there is a source nor there is any sink. So the number of incoming and outgoing lines of force are same. When the number of incoming or outgoing lines are same, lines of force are same, then the net outgoing flux is zero. So according to Gauss's law of magnetostatics, we can say that the net outgoing flux phi b is equal to 0. Equation number 1. Now flux phi b can be represented in magnetic field in the manner that phi b okay, let us write it down again. Phi b is equal to surface integral b dot ds. This is equation number 2. Okay, so now if we substitute this in equation 1, substituting equation 2 in 1, what we get is surface integral b dot ds is equal to 0. So again, it is nothing. It is representing the Gauss's law of magnetostatics only. Fine. So this is equation number 3. Then now what we will be using? We will be using, Gauss divergence theorem. What is the role of Gauss divergence theorem? Yes, very right. It converts surface integral into volume integral. So Gauss divergence theorem, surface integral b dot ds will be converted into volume integral del dot b dv. Okay. So now if we substitute this in the further equation, what we get is substituting. What we get is volume integral del dot b dv. This is equation number 4. We are substituting in equation 3. Del dot b dv is equal to 0. From here, clearly we can see that divergence B is equal to 0. Now, this is showing what? This is nothing but the Maxwell's equation in Maxwell's second equation in differential form. And what does this signifies? It signifies that magnetic monopole does not exist in nature. What does it signify? Magnetic monopole does not exist in nature. So this is the Maxwell's second equation in differential form. And again, we can see the significance of the Gauss's law of magnetostatics is not changing. Maxwell's has written this, beautiful law just in mathematical manner, the differential form. Okay. Next, now we will be deriving Maxwell's third equation. Third equation in differential form. So Maxwell's third equation in differential form. What does the Maxwell's third equation in differential form signifies? Very right. It is, it signifies the Faraday's law of electromagnetic induction. What does the Faraday's law of electromagnetic induction says? According to the law, when magnetic flux linked with the circuit changes, an EMF is induced in the circuit, whose direction is always opposite to the change responsible for its production. So suppose an EMF E, small e, suppose an EMF small e is induced in a closed circuit closing a surface S. Due to change in magnetic flux phi B, this induced EMF will be directly proportional to the rate of change of magnetic flux linked with the circuit. So how we can write this? According to Faraday's law of electromagnetic induction, E is equal to minus d phi b by dt. Okay, where E is the EMF induced and phi b is again the magnetic flux. Okay, phi b is the magnetic flux. So now E can be written in terms of electric field as E is equal to line integral E dot dl. Okay, this is equation 1, this is equation 2. And phi b can be written in terms of magnetic field as surface integral P dot ds. This is equation 3. So I think we can substitute the values from equation 2 and 3 in equation 1. So let us substitute the values. What we get? Substituting, or we can just write, using equation 1, 2, 3. Using equations 1, 2, and 3, we get line integral E dot dl is equal to minus in place of 5e, what we are writing? Surface integral B dot ds. Okay. So we can also write this as line integral E dot dl is equal to minus surface integral del B by del T dot ds. Fine. And this is nothing but equation number 4. Now over here we will be using Stokes theorem that we revised in the first video. Stokes theorem. What is the role of Stokes theorem? It will convert line integral into surface integral. So using Stokes theorem, line integral E dot dl is equal to surface integral curl E dot ds. Now this is equation number 5. Now we can substitute the value from equation 5 in equation 4. So now let us do that. Substituting the value from equation 5 in equation 4. So what we get it? We get that surface integral curl E dot ds is equal to minus surface integral del B by del T dot ds. Okay, this is equation number 6. From here, we can clearly see that curl E is equal to minus del B by. What is this representing? This differential form is representing Maxwell's third equation. What is this? This is Maxwell's third equation in differential form. Okay, again, what does it signifies? It signifies Faraday's law of electromagnetic induction. So in the next, we will be talking about Maxwell's fourth equation. Okay, students.